So for those of you watching the video, a very warm welcome. Thank you for sparing your time. This is going to be a 1 hour session on the subject of mechanical vibration. Excuse me. And the reason why it's called a survivor's guide to vibration is this. I'm sure that there'll be a rich variety of people watching working in different applications areas, different industries. You might be from the automotive industry, the aerospace industry. It really doesn't matter. No matter what industry you are in, the things that you're going to learn about today will be applicable to anything, anywhere. So you should be able to survive if you're taken out of the automotive industry and put into the food and beverage industry. You should be able to survive if you're taken out of the steel industry and put into the aerospace industry, for example. So another aspect of this, of course, is that all of the machines and applications you see on the left-hand side will involve the machines that you see in the middle column. So we have, take for example, the aircraft. We have an aircraft here. It will have on board, obviously, gas turbines to push it through the sky. A power station will have steam turbines. The aircraft will have pumps and fans on board. We'll have gearboxes. Very seldom you get diesels, although if it's a piston-driven aircraft, then it will have a reciprocating machine on board. It's going to have electric motors, obviously. Now, here's the thing. A frequently asked question is, can we measure linear actuators? Things don't have to go around and around to be subject to the laws of physics. So if you're dealing with hydraulics and you're dealing with hydraulic jacks that move in and out, linear actuators, everything you learn today can be implemented in that field. And static objects. So here I have a timing sprocket from a car. You can do tests to it to test its mechanical integrity. So again, the things that we're going to learn about this week and next week can be applied to absolutely anything. Why is this? The reason is that all machines, no matter what they are, obey the laws of physics. Even static things like a pen obey the laws of physics. And the law of physics that they obey, the one that's really interesting to us, is Newton's second law of physics, where force equals mass times acceleration. And we've got a simple experiment here to illustrate this point. We've got a machine in the form of a workshop benchtop grinder sitting on top of some bathroom scales. Now, in this case, the benchtop grinder weighed around about 5 kilograms. And you get a reading on there because gravity, acceleration due to gravity, there's 1g, acceleration due to gravity is pulling the grinder down onto the bathroom scales, and we get a reading of its static mass. So there we have its mass. Now, no matter how hard you try to build your machine and make it a very good quality machine, there will always be some residual unbalance force. So this rotor that's inside this electric machine will have some residual unbalance, a heavy spot. And people spend time and effort to either remove the heavy spot or put a correction weight on the other side, but they will never ever get to a point where there is no unbalance. A gyroscope in an aircraft, for example, is a very finely balanced machine. It will still have some residual unbalance. And in a minute, that heavy spot is going to rotate. We're going to apply some power, and this machine is going to rotate. So the heavy spot, indicated by this little red arrow here, the arrow is pointing to the heavy spot. We impart some energy into the machine, and we can do that in the form of diesel fuel if it's a diesel engine, aviation fuel if it's a gas turbine, coal and steam if it's a steam turbine. We put some energy into the machine, and in the case of the electric motor, we apply electricity, and electromagnetic forces get set up between the stator and the rotor, and this thing starts to rotate. Excuse me. So the heavy spot is going around and around, and as a result of that, it's imparting a centrifugal force. It's trying to throw the machine off its center line, and if we put it on some bathroom scales, the bathroom scales measure in just one plane. It's measuring in the vertical plane. So as the heavy spot is in the upwards direction, it's trying to accelerate the benchtop grinder off the bathroom scales so the reading will go down. And when the heavy spot is in the downwards direction, it's applying acceleration forces into the bathroom scales so the reading will go up. And as that vector, that we call it, rotates, it's rotating through 360 degrees, if we measure in just one plane the forces that are going into the foundation of our machine, you will find that you plot this thing called a sine wave. Now, it's not very easy. I have a machine here. I've got a blue benchtop grinder here. Excuse me. It's very difficult to lift this thing up and put some bathroom scales under it. And obviously, you're going to do it professionally out in the field. You're not going to start putting a set of bathroom scales under the seat of your diesel. But what you can do is lift up the diesel and put force sensors under there. But it's a very invasive and very difficult thing to do. So what do? You go to the shops and you buy yourself an accelerometer. These things measure acceleration. There's a crystal in here that as we move the thing up and down, it creates a voltage in the crystal, and we pick up that voltage with a cable and put it into our instrument. There's a session on transducers coming up in a few weeks' time. For the time being, we're just going to apply our accelerometer that measures acceleration and put it on top of our machine. So just bring it over here so you can see. Or maybe that way. There we go. We can see that. So we've got an accelerometer on our machine. So we've got this thing going around and around. Here's another little diagram courtesy of Wikipedia. We've got this rotating vector. And because the machine is sitting on our bathroom scales, the bathroom scales are measuring in only one plane. So we look at what happens to the reading in on the bathroom scales in one plane. As that vector rotates, the reading on the bathroom scales will go up and down sinusoidally with time. So it's forces that are the root cause of vibration. It's not, vibration is a symptom, it's not a cause. It's forces on our machine that are the cause of all heartache. Now, any mechanical tolerances in the build of your machine that allow movement, you're going to get movement that corresponds to the direction of the force being applied. So if this machine isn't bolted down onto my desk, so it's free to move. So as I spin this machine up, this machine is now going to start moving on its foundation, and I can measure that with my accelerometer. And you can see there's a direct relationship between the force being applied and the corresponding vibration that you get. And if you want to reduce the vibration, one of the biggest, the simplest weapons in your armory is to reduce the forces. For example, if the machine is out of balance, if you balance the machine, you're reducing those forces, you will reduce the vibration pro rata. The value of vibration that you're going to get is proportional to the amount of work being done by our machine. So I have my electric toothbrush here. There's nothing to stop you testing electric toothbrushes. In here there will be an electric motor, but it's a small battery-driven electric motor. So the amount of power, the amount of energy in there is quite low. I expect to see much lower forces, much lower vibration. A bigger machine, even if it's a good quality bigger machine, is going to have inherently greater power, and therefore I expect to see inherently larger values. And if you take this right out to industries where you've got 15 kilowatt motors, 150 kilowatt motors, 100 megawatt generators in power stations, you expect the levels to go up pro rata, or proportional to the size of the machine. Another thing that you need to take into account, obviously, is load. The harder the machine is working, the more current it's going to draw. There's greater work being done, you expect to see the levels go up. A good example would be if you're driving your car along the flat, and then you start to go uphill, you will hear your engine working harder, and you will hear the vibration levels go up. and you have to change gears sometimes to make it easier for the vehicle to go up. And that applies to any application whatsoever. The reason why we do all of this is to detect machine faults, and one of the classics I've already mentioned is unbalance. But the idea is that if your machine is now faulty, we can use vibration to detect that fault. If you're in the business of manufacturing toothbrushes or grinders, you can use vibration to reflect the quality, so you can measure the quality of the machine before you ship it to your customer. And then once your customer has installed the machine and is operating it, you can watch how the vibration deteriorates with time, and that's called machinery condition monitoring or predictive maintenance, whichever name you prefer to use. Great, that's the basics of vibration. We need now to put some units on here, and we can put some units on here with a simple aid of a pendulum. So we've got a pendulum graphic there with great gratitude to Wikipedia again. I am going to use the real thing. I've got a simple pendulum here. Let's get rid of the machine for the time being. I've got a simple pendulum here, and we'll go and investigate the units that we can use. I impart a force, I impart some energy by pulling the pendulum away from my fingers, sorry, away from the center spot, and I'm going to let go and it's going to oscillate. But let's do things slowly. I pull the pendulum over to the right-hand side, and when I let go, this pendulum is going to accelerate away from my fingers due to gravity. So accelerating away from my fingers due to gravity. Due to the fishing wire that I've got, it's constrained to move in an arc, but it's accelerating away from my fingers, and if it's accelerating, it means that the pendulum is getting faster and faster and faster. So it's getting faster and faster and faster. Where its displacement is 0, it's reached maximum speed, and now gravity is going to take over and cause it to decelerate, so it's getting slower and slower and slower, and it will come to a halt here. So when we see a pendulum swinging, our eyes kind of gravitate onto the displacement, the total excursion. We usually measure displacement in microns if it's an electric machine, or if you're working in English unit, thousandths of inches. In this case, it can be measuring centimeters. Our eyes on the webcam are gravitating to the physical displacement of the pendulum. But if the displacement is changing sinusoidally with time, that means that the velocity is changing sinusoidally with time, and the acceleration is changing sinusoidally with time. So for a very, very simple structure here, a pendulum, there are actually 3 parameters I can measure: displacement, velocity, and acceleration, or acceleration, velocity, displacement, whichever you prefer. You can use any one of those 3 as a unit of vibration movement. So that was a pendulum going backwards and forwards. The same applies to an electric machine going around and around. We've got a graphic here. There's my unbalanced spot on my fan going around and around. It causes the shaft of the support of the fan to move, and with 3 parameters occurring concurrently. The displacement is changing with time, the velocity and the acceleration. All 3 parameters are changing simultaneously with time, and we can measure any one of those 3. There is a simple mathematical relationship between the acceleration, velocity, and displacement for a sine wave. So this is sinusoidal motion with time. Don't panic about the math. So I've never worried my heart. If you get really into the subject, the 2 numbers, or the 2 things I remember, are 2 pi f and 4 pi squared s squared. You don't have to remember it. But what this plot is saying is if I use my accelerometer to measure acceleration on my machine, so I've got my machine here, and I'm going to be measuring acceleration, there's a simple conversion that we can use. If we take the acceleration level and divide by 2 pi f, we can instantly calculate the velocity. And if we take the acceleration value and divide by 4 pi squared s squared, we can instantly calculate the displacement. We don't worry you with the math. When you switch on the instrument and push the buttons, that's what it will be doing for you. So you tell it what kind of sensor you've got, You tell it what you want to see on the y-axis, and the box will do this arithmetic. So far, so good. However, excuse me, even though this is a very basic introduction to vibration, one thing that you need to be wary of is the effect that doing this mathematics has on the signal. And I've got a simple demonstration for you, he said. Hope it works this afternoon. It didn't work this morning, so we'll give it a try. I have an instrument here. I have my sensor sitting on top of my machine, but my machine is not running. The machine is stationary. And I'm just going to take a vibration measurement. Don't worry about the buttons. All we're interested in is the display. So I'm going to press start to make it do a measurement. Off we go, and it's going to do some auto ranging, and in the fullness of time we should see a reading. There we go. Let's see what we've got on the y-axis. Excellent. So I've got my sensor sitting on my machine, and we're not seeing an awful lot going on. We've got G on the y-axis, which is the unit of acceleration. So we've got G on the y-axis, we've got frequency on the x-axis, which I'll explain shortly. But you can see there's not an awful lot going on. I'm not getting any reading from this machine, except down at the left-hand side. And on the left-hand side, you can see a little bit of activity on my analyzer. And that activity is coming from planet Earth. These sensors, when you put them onto the machine, aren't just measuring vibration from the machine. The machine is sitting on a foundation, so it's sitting on my desk. My desk is sitting on the floor. I am one story up in my building, so the building is sitting on, in my case, rock, and over in the far distance is a road. And what people don't realize is that, especially out there in real-world industry, where you've got other machinery running, you've got lorries, you might have earth-moving vehicles, your factory might be near a railway line. When a railway train passes by, you're going to get ground-borne vibration. And what I'm doing here is I'm just gently rocking the table, and you can see the level has gone up massively. If I stop bashing the table, the level drops. Now, there's a thing about this, that that seismic vibration that we call it, this very, very low frequency vibration, tends to be always there. And when we convert from acceleration on the y-axis, we've got G, and I tell the instrument I want velocity, we're going to take this signal and divide by 2 pi f to convert. But on the left-hand side of this display, f is going to become a low number. And when we divide a small number into a bigger number, we make that bigger number bigger. So I'm going to do that. What I want you to do is memorize the height of this peak on the left-hand side. I'm now going to ask it to convert from acceleration to velocity, and I'm going to start again. It's acquiring the data. Now you can see that that peak on the left-hand side has become much bigger. If I get rid of the cursor, the peak has become much larger than it was, and I'm not even touching the table. And that's because the effect of converting mathematically from acceleration to velocity exacerbates any low-frequency vibration that we might have. Won't bore you, but if you go on to displacement, where you're going to divide by 4 pi squared f squared, you can forget about it now, we've done with that, it's going to exacerbate that low-frequency vibration even more. And what you'll hear it referred to is ski slope, because it looks like a ski slope in a ski resort. Now, when people write their ISO standards, they know that that's what you could be measuring when you're trying to quantify the quality of this machine, when you're trying to quantify the machinery health of this machine. They are aware that you don't really want to be measuring ground-borne vibration coming up through your machine. You want to get rid of that. So one of the basic things that you're going to be doing when you go out there with your hard hat on, your ear defenders on, and you want to get rid of seismic vibration, we have this thing called a filter. And it's prudent when you're doing machinery-type vibrations that you use a filter. Most ISO standards will tell you to get rid of anything below 10 Hertz, which is 600 revolutions per minute. Beware that some standards say 2 Hertz, but I'm going to use a 10 Hertz filter, and I'm going to press start again. We're off and running, taking our measurement, and yeah, if I zoom in on that, you can see that it's chopped off the signal below 10 Hertz or 600 revs. You're saying, you might be sitting there saying, well, there's still something going on. That is because I'm working with a very, very wobbly desk. My glass of water here is shaking like crazy. My desk is very, very flexible. So it's picking up the slightest movement that I make, and that's spreading across into my measurement. We don't panic, because if I start the machine is now running up. In relation to the vibration coming from my machine, that seismic vibration is really tiny. So there's my seismic vibration down there. Here's my vibration coming from the machine, and the relationship between the two, one is so small, we can more or less forget about it now. Job done. Great. So beware that sensors don't just measure the vibration from the thing that you put it on, it measures planet Earth. Now this is just real data taken from a rope winding machine. You can see in their case the ski slope there, exacerbated when you convert from acceleration to velocity. And we've done that. So you've been looking at a sneak preview of this thing called a vibration spectrum. I'm going to deal with frequency very shortly. For the time being, we're still dealing with the amplitude of a signal, how big it is. We've got this sinusoidal signal going on, either from a pendulum or a rotating machine, and this machine is going up and down. And we're trying to tell you in an engineering report the size of that vibration. So on this thing called a frequency spectrum, we have frequency on the x-axis. On the y-axis, we have the signal that we're trying to measure, either displacement, velocity, or acceleration. And the height of this line that you see is proportional to the level of vibration that we're getting. Now, there's a slight problem here. Going back to our pendulum, it's much easier to explain in the context of a really simple machine. So here's my machine. And it's oscillating backwards and forwards. For simple periodic motion, unfortunately, there are something like 7 different ways that I can describe the size of that vibration. Forget your units, acceleration, velocity, and displacement. I'm just talking about the size of the vibration. When we've got the pendulum oscillating, we could talk about the total excursion from left to right. So in my case, if I get it swinging nice and large, you can see it swinging backwards and forwards. I can talk about the total excursion from far left to far right, and that is called the peak-to-peak value. And on our graph of the sine wave, there it is, the peak-to-peak value. If it's going up and down, you've got motion going up, motion going down, you've got the total peak-to-peak. There is a position of rest, it's acquiescent state, so there it is sitting and doing nothing. And it follows that if it's doing about half a meter peak to peak, it will be about a quarter of a meter peak. The relevance of that, and I've done it again, I've forgotten to bring my visual aid, but no matter. You will find that if you're working to American standards, telling you how much vibration to measure in your machine, you will be required to measure, I think it's velocity, vibration velocity in peak, and you will be required to measure vibration displacement in peak to peak. As I said, I've forgotten the visual aid, so I'll resort to fingers. There is a journal bearing. In a journal bearing, the shaft rides on a film of oil, and you've got these things called eddy current probes that measure the position of the shaft, and you want to know the total displacement of this thing, because if you've got 25 microns clearance between your shaft and the bearing, and you know that your shaft is moving 30 microns, you know that you're getting metal-to-metal contact. So measurements of displacement, peak to peak, in journal bearings is very important, and that's why it's used. By far, the most popular way of describing the actual excursion of this thing is to measure something called the RMS value, the root mean squared. And it's so important that we're going to go through the process slowly. So here is my oscillation. So I'm going to set my pendulum oscillating. And while that graphic changes, what happens if the peak or the peak-to-peak is changing with time? So obviously this value is getting less and less and less with time. You take the maximum value that it was when it was at its worst. With the RMS, what we're going to do is take measurements at fixed time intervals and take those measurements and write them down. So if you're using a dial test indicator, you can do the same with a dial test indicator. You can get your machine, put your dial test indicator on here, get the machine to vibrate, the needle on your dial test indicator is going to move, and you can write those numbers down, take samples. That's exactly what we're doing with a digital instrument. We're taking samples of the data. So we take a measurement at time number 1 and record that at time number 1, and in my case it's centimeters. You take a reading at time number 2 and write that value down. Time 3, write it down, and you keep doing that over a period of time until we have a number of numbers. So we've got a number of values of the movement of our pendulum, and the next stage is to take the average, and another name for average is mean. So we don't panic about the conversion between average and mean, but we take the mean. To get the mean value of something, the time interval is irrelevant. The fact, all you need to know is that you've taken those measurements at a fixed time interval. So we can dispense with the time interval between the readings. We've just got the readings of the amplitude. So we need to take the average. How do you take the average? You add all the numbers together and you divide by the number of numbers. Now, unfortunately, excuse me, this is slightly flawed because half these numbers are going to be positive and half these numbers are going to be negative. Because the pendulum is swinging, if that's your reference position, the pendulum spends half its time going that way, positive, and half its time that way, negative. Or going back to our dial test indicator and you're measuring the movement, the needle's going to go positive and then negative. So for something that's oscillating sinusoidally, you're going to get an equal split, 50-50 split between the positive and negative numbers. So when you take the average of these, the average position of this pendulum is in the middle, no vibration. So you say to your customer, this workshop grinder has absolutely no vibration on it. Wonderful, we'll buy 5,000. Wrong, this is slightly flawed. We need to do something about this. We need to accommodate the fact that the average position is 0. So we need to get rid of those negative numbers. And the way that you get rid of the negative numbers is to square them. If you take -1 and multiply it by -1, you get +1. If you've got -2 times -2, you get +4. So squaring the numbers is wonderful stuff. That's going to get rid of the negativity. And now we can take the average and get a positive value rather than 0. This is slightly flawed as well, because when you square a number, you make the numbers bigger. Oh dear. So squaring is a good thing, and it's also a bad thing because we've made them bigger. I've said that -1 times -1 is +1. Great, we've got rid of the negativity. But -2 times -2 is +4. Oh, it's bigger than it originally was. So the way that we can remedy this situation is, having squared them and taken the mean or average, we can now take the square root of the whole lot, take the numbers back to where they should be, and we end up with root mean squared. The RMS stands for the root of the mean squared. In the space of an hour, I don't have time to bore you with lots of maths, and I wouldn't be interested anyway. So to cut a long story short, the fact that we've taken measurements over a period of time means that the RMS value is proportional to the amount of work being done by the machine. The harder the machine works, the more that the values will go up, and that will be reflected in the RMS. And that's one of the reasons why RMS is the most popular way of describing amplitude. It's proportional to the amount of work done. So if something is faulty, if the machine is going out of balance, it's misaligned, it's suffering from mechanical looseness, the machine is doing more work, there's more energy, that will be reflected in the RMS value, and RMS is a wonderful, ubiquitous parameter to measure. While we're here, we're just going to be careful. I'm interchanging the word amplitude. Amplitude is not a unit. You'll hear people talk about acceleration, velocity, and amplitude. That's incorrect. It's acceleration, velocity, and displacement, because you can have an amplitude of displacement, you can have an amplitude of velocity, and you can have an amplitude of acceleration. So just be careful that you use the right nomenclature. It's displacement that we've got, not amplitude. And it's wonderful stuff. It's a very, very quick and easy measurement to do, and shouldn't be denigrated. Here we've got an analogy. Here we've got a crying, squawking, eating, vomiting machine. And when this thing starts to go faulty, it will start to squawk, and you can test it by taking a very simple measurement, its temperature. And that's the analogy with using the RMS. It's a one-figure number. It's a quick and easy measurement that you can take. And this is built into instruments such as these vibration pens that you'll see on the market. Very often they'll just give you a one-figure number. Where are we? Vibration pen. Here we go. I'll just use my laser pen. So the pen has got an accelerometer in the tip, a battery, and a readout. You can put it onto your machine. The machine will be running. You put it onto your machine, and you get a readout. Very, very quick and easy. And the latest instrument from SKF actually does 3 measurements. It will take a temperature measurement. So when you put the sensor onto the machine, it will take a temperature as well. The overall vibration severity, which you've just seen, and it will also do a measurement of the bearing condition. The reason why it does a measurement of the bearing condition is that you have to be careful about this conversion between acceleration, velocity, and displacement. You saw me back here. I glossed over this little formula here. If you are dealing with sinusoidal motion, so there we've got sinusoidal motion. If you're dealing with sinusoidal motion, it's really easy to calculate the difference between RMS peak and peak to peak. So we've got the RMS value here. If you take √2 times it by the RMS, that will give you the peak. And because the peak to peak is double the peak, if you take 2√2, that gets you the peak to peak. So there's this simple, very, very simple √2 relationship between RMS peak and peak to peak. And a lot of instruments on the market will give you those 3 values. But what you're going to be wary of sometimes, not all instruments do this, but if you set an instrument to peak, it assumes that the bulk of your vibration is sinusoidal and will multiply by √2 to give you the peak value. And that works 90% of the time. So you can sleep safely tonight. The one time you really need to have your wits about you is if you're dealing with a machine that can generate an impulsive type of signal. By impulsive, I mean some kind of tapping signal. And typically, the types of machine that are going to produce a tapping type of signal, are bearings, rolling element bearings. A rolling element bearing, as the ball or roller rides over a spall, which is a bit of damage, you're going to get a tap. And the same will apply to gears. If you've got a broken tooth on a gear, every time that broken tooth comes round, you're going to get a tap. And you can be fooled into thinking that you don't have any damage unless you know what you're doing. And I'm hoping that this afternoon's demonstration works a damn sight better than this morning's demonstration. So we will see. I'm going to give you a little illustration of this. Let's get rid of the moving graphic, and here we are. We're going to do it. We'll minimize that and make this bigger. So I'm going to take an acceleration reading. As I said, don't worry about the spectrum. We're just interested in the numbers for the time being. Let's go back. I've got an accelerometer. I want to measure acceleration. I want to measure RMS. I'm going to measure to 10,000 hertz, which is 600,000 revolutions, and I'm going to get a very fine spectrum. Let's check acceleration. That should do it. Now, what I'm going to do, I've got my machine here. I'm going to simulate damage to the bearing by tapping the machine during my measurement. And we're going to write some numbers down. So I need a pen, I need a piece of paper. So, we'll get that back. So we'll start our machine. We'll start tapping. And we'll start our measurements. And you can see that the value there is 0.3 of a G. 0.3 G RMS. Right, so what I'm going to do now is go back, and I'm going to change from an RMS detector to a let's do a peak detector, just for fun. Variety is the spice of life. So we start our measurement again. And we've got a reading of around about 0.5 G, 0.49. Call it 0.49. So we've got 0.49 G peak. And what I'm going to do now is switch to something called true peak. And do the same again. And that has come out at 2.9 G. I actually read 3 G at one point. If you'll permit me, I'm going to round that up for reasons that you'll see. I'm going to round that up to 3 G. 2.9 G true peak. Switch off our machine. Show you the numbers. So here's my result of my survey. I had 0.3 of a G RMS, then changed the detector to, there we go, changed my detector to peak, and you'll notice the number's gone from 0.3 to 0.49, and effectively that is root 2. Take 0.3, multiply by root 2, you get 0.49. When I change it to true peak, you'll notice there's a world of difference between 0.49 and 3. 0.4, 0.5 G peak, 0.3 G true peak. There's a big difference in that number, almost a factor of 10. Why is this? Well, if you go back to my instrument, there's my spectrum. If you look at what's happening in the time domain, this is the plot of the signal versus time. So we've got the output from our accelerometer versus time, and we can see the impacts. What the machine is doing is taking the RMS of that signal, and I've shown you the RMS process. On this display, there are something like 50,000 measurements. So you've got 50,000 measurements over a 2.5 second period. So we've got 2.5 seconds, we've got 50,000 measurements across that time period, and it's going to do the RMS of that 50,000 readings. But let's count them. We've got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, I tapped the machine 11 times during that 2.5 second period. So you've got 11 big numbers in amongst 11 big numbers in amongst 50,000 smaller numbers. And when you take the average of that, the averaging process will destroy altogether these peaks that you see. So when you're dealing with machinery and you're taking simple readings of machinery health, be careful that those readings of machinery health only work for simple faults such as unbalance, misalignment, mechanical looseness. You have to have your wits about you when you're wanting to check the health of bearings or gears. And you would need to take a separate type of measurement to do that. So far so good, so we've done that. So here's one I prepared earlier. This is genuine data, so I've taken this data and put it into PowerPoint. On this one I tapped twice. So many instruments on the market measure RMS. When they measure peak, they're actually measuring pseudo peak, which is root 2 times RMS. When they measure peak to peak, they're actually measuring pseudo peak to peak, which is the RMS times 2 root 2. But what you want, if you're dealing with impulsive type signals, a tapping type sound, a ticking type sound, you need to measure true peak or true peak to peak. Units, and summary of all of that, units, the unit of acceleration is the G, G being acceleration due to gravity. If you're working to SI units, you're going to use meters per second squared. Velocity is measured in millimeters per second. In SI and ISO units. Displacement, we're not going to be dealing with centimeters or meters. We're generally dealing with microns. So the tingling sensation I've got on my fingertip here, we're dealing with microns. And I said that everything is related to Newton's second law of motion. So you will occasionally measure force, and force is measured in newtons. In America, you will be dealing with G, inches per second. That's a mistake, actually. It should really be written IPS for inches per second, IPS. Thousandths of an inch, but in America they don't call a thou, they call it a mil, which confuses the devil out of Europeans. A mil is not a millimeter. It's not a millionth of an inch. It's a thousandth of an inch. So be wary of that one. You'll see a lot of American standards with mils on the y-axis. It's actually thousandths of an inch, and force is measured in pound force. Remember that when you do your vibration survey and you take a reading in whatever parameter you're using, that you write down what's called the detector. Because this machine might be doing something like 5 millimeters per second RMS, but unless I write down this little bit of information on my report, RMS, that value is meaningless, because there's a world of difference for the same reading between RMS peak and peak to peak. 5 RMS is 7 peak is 14.14 peak to peak. So make sure when you're writing down numbers, you write down what's called the detector. So far so good, won't bore you with those. There's some simple conversions. Time's marching on. Which parameter do you choose? When you're standing in front of the machine, you've got your shiny new instrument, you're going to do some measurements, you've placed your sensor onto the machine, and you're going to do some readings. Which parameter do you choose? Acceleration, or do you choose to measure velocity, or do you choose to measure displacement? Well, the get out of jail free card, for those of you who play Monopoly, is the standard will usually tell you what to measure, so that ISO 10816, Part 3, which is for general industrial machinery, will tell you to measure vibration velocity from 10 Hertz to 1,000 Hertz, and also to measure vibration displacement. If you've got a product where you can't find the ISO standard, there's no ISO standard to tell you how much vibration to expect from a toothbrush, or a lot of machinery out there in industry, if you don't know which one to measure, the objective of these next few slides is to tell you how you choose. And we're going to do another experiment. We've got a constant displacement machine here. We've got a table which we can shake up and down. We've got a cog with a pin in a slot, and as this cog rotates, it's going to make this shaker table move up and down. We've got a variable speed machine here, variable speed drive, so we can make this shaker table go up and down with a constant displacement, but with a varying speed. And then we're going to do the mathematics. We're going to take an accelerometer measurement and convert. We're going to convert between acceleration, velocity, and displacement to various speeds as we get faster and faster and faster. And you may well be sitting there thinking, heck, this is a bit hypothetical. No, we're talking about reciprocating machines. A reciprocating machine, whether it's a diesel engine, a reciprocating pump, any machine that goes up and down with pistons in a cylinder, that is a constant displacement machine. It's constant displacement because there's a conrod in there, and if the displacement isn't constant, your conrod is broken. So we're talking about reciprocating machines, diesels and reciprocating compressors. And, excuse me, sorry about that. So we're going to do our experiment. We're going to have our diesel. We might stick our accelerometer onto the engine block of our diesel-driven car and take our car for a drive. And we look at how the amplitude of the signal changes with frequency. So on the x-axis in these graphs, we've got vibration frequency in hertz. On the y-axis, we've got the three parameters, acceleration, velocity, and displacement. My starting displacement is 100 microns, and that is just general vibration. If you put your finger on your engine block when it's not hot and it's just ticking over, the tingling sensation that you'll get on your finger will be about 100 microns. We're going to change the graph paper from linear graph paper to logarithmic graph paper. So log graph paper is very popular out there. It has two advantages. Things that are very small, so we can't see the 100 microns on the left-hand graph, but logarithmic graph paper makes small things look big. So now we can see our 100 microns, and it makes curves become straight lines. Brilliant. So we're sitting at the traffic lights with our engine ticking over at around about 600 revolutions per minute. We've got about 100 microns of movement on our engine block, and therefore we're going to have, if you do the math, 2 pi f, 4 pi squared s squared, you're going to have around about 10 millimeters a second and less than 0.1 of a g. Now we're going to be chronically stupid, and we're going to go down the freeway and put our foot flat to the floor and try and get our engine to go as fast as possible way over the red line. We're going to be up here on the right-hand side, up at 100,000 revolutions per minute. It doesn't particularly matter about the speed, but we're going ultra fast. That engine is going around as fast as it possibly can. I know that in Formula 1 racing, for those of you who are into Formula 1, I think the pistons are only moving 10 centimeters or something like that, sorry, 10 millimeters, something like that, small number, but they're rotating at 20,000 revolutions per minute. You can get these things, but you're talking about very high forces, as we're going to find out. So we're hurtling down the freeway, irrespective of the speed cameras and the police force chasing us, hurtling down the motorway with our engine screaming its head off at very high revs. If we had 100 microns of movement on our engine block, we would have between 1,000 and 10,000 millimeters per second, and we're going to have between 10,000 and 100,000 G. Now, you expose anything to 10,000 to 100,000 G, and it will shatter. It will break. The casting of your engine block will break. Your conrod is going to shear off and break, because machines, just simply normal industrial machines, some special machines can, highly hush-hush, normal industrial machines just cannot cope with levels of 10,000 to 100,000 G. So what do? You put a red line on the red counter of your engine to say, do not take this constant displacement variable speed machine beyond this red line, otherwise there's going to be a loud bang and your engine will explode. What's the moral of this? Well, the moral is that if you're dealing with reciprocating engines, you tend to measure vibration displacement or velocity. There's not very much acceleration there. Yes, that's right. You tend to measure vibration, displacement, or velocity. And we'll come on to the other part of that when we come on to a constant velocity machine, which we're going to do now. So the other popular type of machine are machines that simply go round and round. You haven't got a piston where something explodes, bang, the piston goes down, comes back up, bang, piston goes down, comes back up. You've got something that's going up and down. You've got these machines that just simply go round and around. Gas turbines, steam turbines, and electric motors all just simply rotate. And if you were to take a electric motor, steam turbine shaft, the impeller out of this gas turbine, and manufacturers actually do this, they'll put the rotor into a vacuum chamber, huge great things, suck out all the air, put the shaft on really frictionless bearings. They've taken the air out so there's no drag due to aerodynamic forces. This thing's running in a vacuum. If you run the shafts of any of these machines in a vacuum on specialized bearings, you will find they behave as constant velocity machines. So here I have, at my right hand side, a constant velocity machine in the form of an electric motor. If I was to spin this thing in a vacuum and I was to measure typical background vibration levels, I've got a typical reading, 5 millimeters per second. We'll do the same experiment. We'll go through a range of speeds. So this thing's running fairly slowly, down at 600 revolutions per minute, at 5 millimeters per second RMS on my bearing. I would have around about 100 microns and less than 0.1 of a G. I now speed this thing up to incredibly high speeds. Dentist's drill, 200,000 revs. Turbocharger inside your car, 200,000 revs. Gas turbines, there's a lot of gas turbines running at very high speeds. And gear mesh frequencies. Bull gears, for example, the gear mesh frequency, the rate at which teeth are meshing, can be hundreds of kilohertz. So we're on the right-hand side of the spectrum. If I had a gearbox, a turbocharger, dentist drill with 5 millimeters per second RMS on it, I would have 0.1 of a millimeter, which is a microscopic displacement, very difficult to measure, but I would have between 10 and 100 G. Sorry, 10 and 100 G. So whereas on my constant displacement machine I had 10,000 to 100,000 G and the thing broke, with a constant velocity machine we've got 10 to 100 G and the thing doesn't break. The American Gearbox Manufacturers Association says 11 G for a gearbox and we're happy. So this chart, if you're working at low frequencies, medium frequencies, you tend to measure velocity displacement. If you're measuring at ultra high frequencies, you measure velocity or acceleration, and away you go. The reason why velocity is used is that it's independent of machine speed. So if you said to me, come to America, I've got a machine that's running with 5 thousandths of an inch, what's that? That's 250 microns, 5 thou movement, I couldn't say whether that's good or bad unless I know the machine speed and the machine size. If it's a forced draft fan in a power station, 5 thou movement isn't very bad. You expect a huge, great fan to be moving that much. But if it's a high-speed turbocharger, I wouldn't be standing near to that turbocharger because you'd be having lots and lots of G. I think we've got 10 minutes to run and then we're done. So now you're armed with enough information. We're going to measure acceleration, velocity, and displacement with the appropriate detector, RMS usually, sometimes peak if you're working to American standard. You get your simple vibration meter. You have a machine, and the way you do it is to start at the non-drive end and work your way to the driven end. So you've got motor, non-drive end, motor, drive end, pump in this case, driven end, pump, non-driven end, and you would take a series of measurements. In my days, it was nice and easy. You would just take velocity, Modern standards now ask you to measure displacement as well, and you would be taking a separate measurement of bearing health with the appropriate measurement. We're going to do a session on bearing measurement under the title of acceleration enveloping. So these things are wonderful. The vibration pens, they take a reading for you, the same as we've got here. They take a reading, compare that with the ISO standard, ISO 10816 Part 3, tells you the grade, tells you the levels coming off the bearing, and tells you the temperature. Wonderful things. You do have to be a little bit careful. I haven't got time to talk about standards, do I? I haven't got time to talk about standards. I'll skip standards. You do have to be a little bit careful that overall vibration measurements can be fooled. I've mentioned the fact that they can be fooled by impulsive signals, so you do acceleration enveloping. They can also be fooled by frequency content. I won't bore you. Should I bore you with a demonstration? I will. Let me bore you with a demonstration. I have a noise source here. I've got a radio that produces what we call white noise, and I'm going to take a noise measurement from it with a simple sound level meter. So I've got my white noise source here. I've got my simple sound level meter that's going to give me a reading. I'm going to put this onto C weighting, and we'll put it onto a slow reading. So I'm going to take what I'm going to do is create a noise, and then I'm going to create a tonal noise on top of it and take a reading. So I'll switch that on. So start with the bass reading. So that bass reading is 91.7. Do it again. .5. And now I'm going to do the same again, so whistling. It's actually gone down. .5. So as far as this sound level meter is concerned, it was 90.5 with the hitting sound, and it was 90.5 with me whistling on top. And hopefully you should have heard me whistling over the internet. So this is another demonstration of how the overall reading can be fooled by a tonal signal that is tiny in relation to a bigger signal. And that will become apparent when we do a frequency analysis. So the last thing we need to learn about, I'm going to be finished by 10 past, I'm sorry I'm overrunning. The other aspect that I've kind of glossed over in our frequency spectrum is the periodicity. We've got this sine wave. The other important aspect to this, we've talked about all the ways we can measure amplitude. The other important information is the periodicity. What's the time interval of the oscillation? And we plot the amplitude on the y-axis, the vertical axis. The bigger the peak, the higher the vibration, and we plot the frequency on the x-axis. So the higher the frequency, the further on the right we're going to be. The lower the frequency, the further on the left we're going to be. And if we have something that's varying in speed, you'll see these peaks move left and right. It's entirely up to you whether you work in hertz, which is cycles per second. I'm a hertz man. Or if you're a rotating machinery person and you want to relate to your machine in terms of revolutions per minute, we can multiply hertz by 60, and that gets us revolutions per minute. And it's up to you how you scale your x-axis. There'll be a switch to convert. Now, the general idea in frequency analysis is that you put a sensor onto a machine. In this case, it's a motor-driven gearbox. You're going to pick up not just one frequency, as we have with our pendulum, but you're going to pick up lots of frequencies. We're going to have the unbalance of the electric motor coming through the structure to your sensor. We're going to have the gear mesh frequency coming through the structure through to your sensor. We're we're going to have the unbalance of the driven shaft coming through the structure out to your sensor. You see your sensor is going to measure more than one frequency. If you look at the overall signal, which we can see here, here's a real-world signal from my electric motor. All those frequencies are joined together, and they become rather a complicated line. And with the limitations of PowerPoint, that's about as complicated as it can get. But what we have is we have this magic thing called a frequency analyzer, bless them. We do a thing called a Fourier transform, which we'll learn about in 4 weeks' time. And that does the maths for us, converts the amplitude versus time for the electric motor to a line in the spectrum, does the same for the gear mesh frequency, puts it in the spectrum, does the same for the driven machine, converts from amplitude versus time to amplitude versus frequency. And the general idea is that if there's something going wrong with the gears, for example, if they're wearing, there will be higher forces equals higher vibration, and we should see that peak growing with time in our spectrum. So that the fundamentals of diagnostics is to understand what's inside your machine and look for the corresponding frequencies in your frequency spectrum. This nicely gives me the opportunity to explain the relevance of the sound level meter and radio test, because if we are dealing with gear mesh frequencies, these signals can be really tiny. By the time the signal has traveled through the steel of the gear, into the steel of the shaft, through the inner race of the bearing, through the grease, through the ball, through the grease, through the outer race of the bearing, into the casting, through the casting, out through the paint, that signal can be really tiny. And if it's really small in relation to the unbalance, for example, it will not show up on your RMS reading. You have to do frequency analysis, again, if you're interested in gearboxes, because this peak could be quietly growing on you and you won't see it growing. Now, one really simple weapon in your armory for the last 3 minutes is to show you a simple way of looking at peaks. There's the difference between a logarithmic and a linear scale. So I'm quickly going to take a velocity reading. We're going to measure RMS. We're going to measure to 400 Hertz because I'm a Hertz man. So we're going to do a simple velocity reading on this machine. So I've got my accelerometer, I've got my analyzer. I will start my machine. It's running up. Got to steady state. I press start. Brilliant. So there is my peak due to my unbalance. I'll just apologise. I will get rid of averaging so I can just quickly show you something else. So we'll just change that. Oops. Sorry. Start again. It's a ploy to get a drink of water. Right. So there's my frequency spectrum with vibration velocity on the y-axis, vibration frequency on the x-axis. There is your peak. If I stop the machine and it starts to slow down, that peak is going to start moving left in the spectrum. So you can see it's moving left. But the thing I want to illustrate, to switch it back on, is if I look over here on the right-hand side, there's a little peak there that's showing its head occasionally and it's going back down. Now, I haven't got a gearbox, so clearly that can't be gear mesh frequency. But in this case, this is a single-phase induction motor, and what you should find is that that is the pole passing frequency of the induction motor. And it's a tiny, tiny signal that you wouldn't know it was there if you weren't looking for it. You don't have to use high-tech technology. One thing we can do is change the graph paper from linear graph paper to logarithmic graph paper. So with a bit of luck, when I change, what I want you to do is have your eyes fixed to this area here in the spectrum. I'm going to change from a linear graph paper to a logarithmic graph paper. So look in the right-hand corner here, and there we go, bang. We can see that peak much clearer now, and I can use something called a harmonic cursor. If I press the 4 key, and we can tune through, and it will show you that if you count out the frequencies, it will show you that if there were 9 rotor bars on there, 9 times 50, that is your rotor bar passing frequency. Can't see it with a linear graph paper, but you can see it with logarithmic graph paper. Phew, overrun by 10 minutes, I apologise. I think we've broken the back of it. Let's go back to my, so there we go. I should actually have had a 1 kilohertz frequency range, but no matter. That's it. So for the benefit of those of you who are watching the recording, thank you for sparing your time. Next week we're going to be doing fundamentals of structural testing. So thank you, cheerio.